Hello student, to the Foundation of Classical Electrodynamics course. So today under module 2 we have lecture 47, and today we will going to continue the problem that we discussed in the last class, that is the electrostatic boundary value problem, and also try to do another to solve this kind of problem with another method called image method. So let us start. Class number 47 today, and we already started the boundary value problem. So let us continue with another problem. So I am doing all the problems so that you can understand that how to deal with this problem by just exploiting the Laplace's equation in different coordinate system. So the problem is like that: a metal sphere which is uncharged metal sphere means essentially it is a conductor of radius r placed in an uniform electric field say this uniform electric field is say E, which is constant, and along say z direction k. So the question is, what is the potential outside the sphere? That is the question. So that means I have, let us draw the coordinate system first. This is my z direction, say this is my x and y, and suppose we are having a sphere like this. And it is in constant electric field. So the electric field, if I draw, say, is along this direction. So these are the electric field, but since it is a conductor, so what happened? So some plus charge will accumulate here, and some minus charges will going to accumulate here. And the field lines, if I look, it will just go like this. Okay, field line I am drawing in different color. So let us like this. So this is the I mean, along this direction we are having our electric field which is constant. Okay, so this is the scenario we are having right now. So, the total potential, so we need to find out the potential. So, the total potential will be phi, that is equal to phi 0 plus phi I. What is phi 0? Phi 0 is the potential due to E 0, which is already there, and phi I is due to potential due to the induced field, because there is a charge separation. So, some field is being induced. So, due to induced field. Okay. So, K 0 so E 0 K, that is simply del phi del z K, right. So, phi 0, because I consider the constant electric field, the potential is due to the constant electric field related to the constant electric field is phi 0. So, this should be the equation. So, I can, so E 0 is known. So, I readily find out what is my phi 0. So, phi 0, if I integrate, it should be minus of E 0 z plus a constant c, and this z I can replace in terms of r theta coordinate, because this is spherical symmetry. So, this is simply minus of E 0 r of cos theta plus c. Now, what is my phi I? That I can calculate, because the value of phi I, the field due to the induced the potential due to the induced electric field, the solution, because that leads to the, I mean the Laplace equation leads to that potential. So, I can have the direct solution for that, and this direct solution we derived in the last class. It is A L r to the power L plus B L divided by r to the power L plus 1, and then it should be P L cos theta with L goes to 0 to infinity. So, that is the general solution, we already derived that. Now, r tends to infinity, my field need to be 0. That condition readily gives us that A L is equal to 0. That is the boundary condition that I am putting right now. So, my field phi I, which is a function of r and theta, simply becomes summation over L B L r to the power L plus 1 and then P L cos theta. This is the value. Okay. Now, at r equal to r, that is over the sphere, because the radius of the sphere is r. I think it is given in the problem. Yeah, here it is given, the radius is r. So, this is r. So, over the sphere, we know the potential has to be 0, and if that is the case, then I just simply put the phi I plus phi r, phi 0 plus phi I at r equal to r is 0, because this plus this is my total phi. So, phi at r means this plus this at r equal to 0 is 0. So, what is my phi 0? It is E 0 r cos theta plus c. So, I just simply put this value by replacing small r to r, smaller to big R, then it becomes minus of E 0 r cos theta plus c plus, I should have integration, I should have summation L 0 to infinity, then I have BL divided by r to the power L plus 1, just replace small r to r, then PL cos theta equal to 0. Okay, now the next thing is straightforward, because in the left hand side we have a polynomial of cos theta and right hand side it is 0. So, if I manage to find out the coefficient of cos theta for both the sides, then I can get the result. So, what I do, I will going to equate. So, equating the coefficient of PL cos theta from both the sides, we have, so left hand side what we have, minus E 0 r cos theta, then c as usual, then I have, let us expand few terms. So, I have B 0 divided by r, that is the L equal to 0 term, because P 0 is 1, then I have plus B 1 divided by r square, and then cos theta, because P 1 is cos theta, and then rest of the term I should put as usual. L now goes to 2 to infinity, because I already take L 0 and 1 outside. So, it should be B L divided by R L plus 1 and P L of cos theta equal to 0. Okay. Now, rearranging few term, because here we have cos theta and another cos theta is sitting here. So, I just rearrange the term. So, let put all the constant together. So, C plus B 0 divided by R, and then cos theta, then cos theta, and then B 1 divided by r square minus E 0 r, then plus rest of the term, L goes to 2 to infinity, then B L divided by R L plus 1 P L cos theta is equal to 0. Okay. So, now you can see that in the right hand side we have 0. So, that means, and it is true for all the cos theta, all I mean any value of cos theta, any value of theta or any value of cos theta. So, that means this is individually 0, this is individually 0, and all B L should be 0 when L is greater or equal to 2. So, what I get? I get C plus B0 divided by R is 0. I get B1 divided by R square minus E0 R is equal to 0, and BL, where L greater than equal to 2, is 0. In this kind of problem, in most of the cases you find that initial few terms are there, but rest of the term are normally 0. So, if that is the case, I simply have my phi r theta to be phi 0. What I get here? Phi 0 plus phi r. So, I simply have phi 0 and then B 0 divided by R plus B 1 divided by R square cos theta, because all the BL L greater than equal to 2 is 0. So, that should be my term. Now, I know that what is then I put simply minus of phi 0 minus of E R cos theta and plus B 0 divided by R and minus B1 B1 I can find it from here, that B1, let us put B1, how much? It should be E0 R cube, and my C is minus of, so here we had a C, mind it. So, this C is from here, my C was minus of B0 divided by R. So, that term I now put here, the C is minus of B0 divided by R, that is one term, and another term is B1 divided by R square. So, B1 is plus B1 is E0 R cube divided by R square and cos theta. Okay, so everything I try to write in terms of B0 and only one constant. Now I eliminate all the other constant, putting the boundary condition, and eventually I have 1 by R minus 1 by R, and then I have B0 plus E0 cos theta. If I take common, then I have say R cube divided by R square minus R. So, that is my potential at any point R theta, but still B0 is there. I need to determine the B0. So, one of the way to determine the B0 is the total charge, because the total charge here over this sphere has to be 0, and that condition may leads to the value of B0. So, let us try to find out that how to get that. So, the total charge of the sphere so the problem is how to find B0. So, the total charge will be Q equal to integration of sigma ds, because sigma is a charge density and that is 0. And we know the relationship with the charge density and the potential, because E for conductor, just above the conductor, the value of the electric field is this, and we will going to exploit this expression, and that simply gives us phi del r at r equal to r. That should be the expression where we can relate the surface charge density with the potential. Now phi is known, so if I make a derivative with respect to r, so this is my phi. So if this is my phi, so I can make a derivative with respect to r, and if I do, I will going to get this b0 divided by r square with a plus sign, because r is in denominator, and then plus 2 of E0 cos theta, and then r cube divided by r cube, and then plus E0 cos theta. I need to evaluate everything at r equal to r point. So that eventually gives me b0 divided by r square plus, this will be 1, and we have 3 E0 cos theta, that we will get. Okay, so from here I have my sigma. So now the total charge, if I calculate for this sigma, it should be integration of sigma and ds in the spherical coordinate system over the surface. It should be r sin theta d theta d phi, r sin theta at over the surface we are calculating. So over the surface we are calculating, so that should be the value. So well, okay, so now we have so okay, it is no, it should be r square, because it is a surface. So it will be r square sin theta d theta d phi. So because it is a surface, so my q, then I have r square 0 to 2 pi, and that is d phi, and then integration 0 to pi. Now you can see sigma is a function of theta, right? So here you can see sigma is a function of theta. So the integration, the sigma should be inside the integration of the theta. Apart from that, we have a sin theta term here. So sin theta d theta, sigma theta, sigma function of theta, sin theta d theta. So that value is, from here we have 2 pi, so we have 2 pi r square, and then integration 0 to pi sigma theta. If I write that, we already calculate, and that value is b0, what was sigma, b0 divided by r square. Sigma I need to multiply it, because it is sigma by epsilon 0. So sigma has to be this multiplied by epsilon 0. So b0 divided by r square, and then plus what we get 3 E0 E0 epsilon 0 and then cos theta, and then I have one epsilon 0 multiplication here and then sin theta d theta. Okay. So, finally, if I execute this integration, we have 2 pi r square, and then if I took this epsilon 0 for the first integral, okay, let us make like this, epsilon 0 b 0 divided by r square. If I put outside, then the integration simply give us integration 0 to say pi sin theta d theta, and another is plus 3 of E0. Oh, epsilon 0 I take common, so I should not have epsilon 0 anymore here, because I write epsilon 0 outside, right. So, it should be 3 E0. So, it should be 3 E0 and then epsilon 0 divided by no, here we have cos theta sin theta. So, we can write that it is, divided by say 2, and then it become sin 2 theta, and if I make d of 2 theta, then another 2 I will put here, integration 0 to pi. Okay, because cos theta I can sin theta cos theta multiplication, I make a half, and then it should be 2 sin theta cos theta, then it will be sin 2 theta. Yeah, that is the result. So, now we have 2 pi r square. So, these 0 to pi sin theta, if I integrate, I should not have any value. So, here this will be cos theta, and I have 2 here. So, eventually this will be 4. So, I have 4 pi r square, then epsilon naught b 0 divided by r square plus 0, because this integration, and that is the total charge, and that is 0. Since this is 0, after doing all these calculation, we find that b 0 is nothing but 0, as q equal to 0. So, finally, I will put here the value, finally, I put here the value b 0, because b 0 is 0 again. So, my result will be only this part. So, finally, I can get the value of phi as my final result, phi r theta is equal to E 0 cos theta r cube divided by r square minus r. Note that from here you can check it that phi at r is 0, which should be, because if you put r equal to small r equal to big R here, and then it should be r minus r, so it should give you 0. So, it seems that my potential whatever I calculated is correct. Okay. So, next we will extend this boundary value problem, and we are going to learn another method, another important method. In few cases also we are going to use this method, and that is called the image method. So, we called it image method. So, image method is another way solve the boundary value problem. Another way to solve the boundary value problem. So, this method is useful for problems, generally is useful for the problems consisting of point charge near conductor. So, when a conductor is there and again you place a point charge near that, and then if somebody asks what should be the potential and all this, then this kind of image method, the procedure is very useful. So, let us try to do with certain examples. So, few examples. So, the first example is the point charge in front of an earth conducting plane. So, point charge is placed in front of an charged in earth, sorry, not charged, it is earth, that has been grounded. Conducting plane. Okay. So, so let us put a point charge. So, let us draw this how. So, suppose I have a coordinate system like this, and okay, just this. And I have a plane here like this, and a point charge is placed somewhere here, whose coordinate is say 0, 0, D, where this is my z axis, say this is x and this is y. So, this is my plane. Plane is in xy over xy, and this distance is d from here to here. So, the problem is what is the potential above the plane? That is the problem. What is the potential above the plane? Okay, and this is grounded, mind it, this is grounded. Since this is grounded, so the first boundary condition that we have is phi on this thing, on this plane is 0, because this is grounded. So, let me jot down the boundary conditions that we have here. So, the first one is that phi at z equal to 0 is 0. I just wrote it here. Second, the trivial boundary condition that phi when r tends to infinity has to vanish when r is very greater than d. I am far away. If I want to find out what is the potential, then that should be 0. What is r here? R is simply x square plus y square plus z minus d and then whole to the power square of whole to the power half. So, let us put a third bracket here. So, this is my r. So, far away from this point, from here it is a far away point, and this is. So, now the equivalent, now in the image method what we do, we instead of having this system, I have an equivalent system, and the equivalent system is this. That is why it is called image. We consider a image of this given charge just below to the plate. So, the equivalent system is whatever the system, whatever the problem is given, the equivalent system is something like this. So, suppose this is my coordinate, this is y axis, this is x axis, this is z axis. Already this charge is placed here at a distance of d. The equivalent system is saying that let us consider a equivalent charge here in the opposite direction with minus q. Okay. So, whatever this system, so this system is such that it satisfy all the boundary condition that is given, and for this equivalent system if I want to find out the potential, then that should be the same potential if I have the original system which is given here. So, let us do that. So, if I calculate the phi now for this system, it should be the contribution of the two charge. So, phi 1 plus phi 2, the superposition. So, that value is simply 1 by 4 pi epsilon naught, and then it should be q divided by r 1 minus q divided by r 2. What is r 1 and what is r 2? The r 1 and r 2 is, r 1 is x square plus y square plus z minus d square whole to the power half, and r 2 from the minus q charge, the distance, it is x square plus y square plus z plus d whole square whole to the power half. Mind it, the coordinate of the plus q is 0 0 d, and coordinate of the minus q is 0 0 minus of d. Okay. Now, the boundary condition 1 and 2 satisfy by the potential. If you look carefully, that when z is equal to 0, that is if I put z equal to 0, then r 1 and r 2 are same, the phi will be 0, and also if r tends to infinity, then the phi is infinity. So, the whatever the boundary condition is there, it is satisfied by this equivalent system. So, that is the important part. So, the induced, now let us find out what is the induced surface charge, because if you put a point charge here q, and if you have a conducting plane, then some induced charge will be there, and that induced charge we like to find out first. So, so the induced surface charge is sigma equal to minus of epsilon 0 del phi del z evaluated at z equal to 0. Standard formula that we are also using in the previous problem and also the problems in. Now del phi del z, because phi is known, so del phi del z is simply 1 by 4 pi epsilon 0, and then del phi del z will be minus of q z minus d, it should go up, and in the denominator I should have x square plus y square plus z minus d square whole to the power 3 by 2, and then here I have plus of q z plus d, and then I have x square plus y square plus z minus z plus d square whole to the power 3 by 2, and that is my derivative. Now this derivative we will going to execute at the point z equal to 0. So that simply gives me 1 by 4 pi epsilon naught, and then z equal to 0. So this quantity, so it I have a 2 here, so it is simply 2 q d and divided by x square plus y square plus d square 3 by 2. Now my sigma is how much? Minus of 1 by 2 pi, and then q d divided by x square plus y square plus d square whole to the power 3 by 2. Just use the formula sigma is equal to minus of, so I just multiply minus of epsilon 0, epsilon 0, epsilon 0 will going to cancel out, and then 1 4 will be cancelled out by these 2. So this 2 is here. Now what is total charge? That is the thing. So total charge should be integration of sigma and ds, where ds is the surface element over the xy plane, and in so ds should be simply r dr, d phi, r dr d phi. So now I have here sigma, so my q should be minus of q d divided by 2 pi, and I need to integrate. Now I change my coordinate because here x square y square is there, and but ds I write in terms of r phi. For my convenient I did it. So I need to write my x and y, because x square plus y square is r square, so that I can use here. So it is r square plus d square whole to the power 3 by 2. I can write r square as x square plus y square here. So now I can, so what is the integration? Okay, so now I can write it as minus of, see this is over surface, this integration is over surface. So I need to put the proper limit. So that is 0 to 2 pi for phi, and 0 to infinity, because this is infinitely extended plane, r dr divided by r square plus d square whole to the power 3 upon 2. This integration is very much doable, so I can have minus of q d divided by 2 pi, and then from here I have another 2 pi, because I am going to integrate d phi here, and this integration if you do, because if you take r square plus d square to be x, then 2 r dr will be here. So, then you can able to find out the value of this integration is minus of 1 divided by r square plus d square whole to the power half with the limit 0 to infinity. Now, if I put this in limit 0 to infinity, I simply find that this 2 pi will going to cancel out. It is minus of q d into 1 upon d. So, d will going to cancel out. So, eventually I get minus of q, and that is expected, because if I put a q here, so the induced charge here, whatever the induced charge should be minus q, and that induced surface charge, and that precisely we get by exploiting the potential. So, how we get this minus q? We get that the minus q we get by just exploiting the value of the phi that we calculated using this superposition principle. So, that everything is in right place, and using that actually we find that the total potential, using this simple image method, we find that the potential at any point can be represented by just simply making an equivalent system where we have a plus q and minus q. Instead of having a infinite plane, I just replace the entire infinite plane to an image. So, that is why it is called image, as if I am having a mirror here and a plus q is imaged here with a negative value, and then it satisfy the boundary condition, the two boundary condition which is marked here, and then we find the potential, and exploiting that potential we find the induced surface charge is also becoming q equal to minus q, which is expected. So, this is a elegant way to solve again the boundary value problem. So, today I do not have much time to extend to show you this process to show another problem, but next class I will like to show another problem, and that will be the end of our module 2. After that we are going to start module 3, where we understand the magnetostatic problem. So, with this note, let me conclude in today's class. Thank you very much, and see you in the next class.